Hello, this is video 16 for section 7.4 for Math 196. This chapter is on permutations and combinations. Pretty cool stuff. We'll start with an introduction to what a factorial is, which is mainly focused in problems 1 through 12 in the book, and then on the definition of permutations and combinations, which is problems 13 through 20. Then we'll talk about how to identify a permutation and a combination and what the difference is between the two, which is seen in problems 25 through 34 and 51 through 56. We'll then do some applications of the permutations and the combinations using a deck of playing cards, which is problems 37 through 40 if you're unfamiliar with that. And then finally we'll do some other applications that involve the counting principles that we saw in section 7.3, which is we'll see in problems 41, 42, and 61 through 70. So let's start with the definition of a factorial, problems 1 through 12. The definition of a factorial in the simplest terms is a number multiplied by the number before it, all the way down to 0. Well, all the way down to 1. If we did all the way down to 0, then we would get 0, because anything multiplied by 0 is 0. So we should know a few things, like 0 factorial equals 1, which is just a thing that we do. So example 1, 10 factorial over 5 factorial. So we have 10 factorial over 5 factorial, dividing. We can rewrite 10 factorial as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then divided by 5 factorial, which we can write as 5 times 4 times 3 times 2 times 1. And then we cancel out these. These all cancel out. And we're left with 10 times 9 times 8 times 7 times 6, which equals 30,240, which we will later see as a permutation of 10p5. So when we did the problem doing the factorials, we stopped at 1. So we had 10 digits up here, 10 numbers multiplied together, divided by the 5 numbers down here. 5, 4, 3, 2, 1 all canceled out, and we were left with 10 times 9 times 8 times 7 times 6, and that's how we got the answer, which is pretty cool. Okay, the definition of permutations and combinations as seen in problems 13 through 20. A permutation is a set of distinct objects in an arrangement of the objects in a specific order without repetition. A permutation of a set of n distinct numbers taken r at a time without repetition is an arrangement of r of the n numbers in a specific order. So if we have n things and we are choosing r of them. A combination is a set of n distinct objects taken r at a time without repetition and is an r element subset of the n elements. Here, the arrangement of the elements in the subset does not matter. But again, we have n elements and we're choosing r of them. The difference between permutation and combination is that with permutations we will have, I guess to explain it better, our order matters, I guess. So our two equations for permutations and combinations is n factorial over n minus r factorial is permutations, And NCR for combinations is n factorial over n minus r factorial r factorial. So the number of combinations you have is always smaller than the number of permutations you have, because we're getting rid of those repeated choices, I guess. On your calculators, you should have a button that either says NPR or PNR, and the same thing for combination. You should have NCR or CNR, and those you can use those for permutations and combinations. If you have a TI-83 calculator or above, if you click the math button, which is right below the second key, and then hit the right arrow 3 times to get to the probability window labeled PRB, you'll see that the second one on the list is NPR, which is your permutations. The third one in the list is NCR, which is combinations, and the fourth one is factorial. And so that's how you get to those on a TI-83 calculator or TI-84 or those kinds. So our example for this problem is P11.6, or 11P6. So here N is 11 and R is 6. So we write that. So this becomes 11 factorial over 11 minus 6 factorial, which is 11 factorial over 5 factorial, which is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 times 4 times 3 times 2 times 1. All these cancel out. Not the 6. The 6 stays. Sorry. So we are left with 11P6 equals 11 times 10 times 9 times 8 times 7 times 6. So when we're choosing 6, we have 6, we go down 6 from 11 in the factorial. And when you multiply that out, it is 332,640. And if you do it on your calculator, it's 11, then find the NPR button, 6, and you should get the same answer. That's for calculator. And then our second example, which is C11C6. N is still 11 and R is still 6. So our equation is 11 factorial over 11 minus 6 factorial times 6 factorial. Yeah. So that's 11 times 10 times 9 times 8 times 7 times 6. Because this part, I guess, this part of the equation, we already did. That is our permutation. Oops. That part is our permutation. And then we're dividing by 6 factorial to get rid of the repetitions. So times 5 times 4 times 3 times 2 times 1. If you multiply that out, you will end up with 462. And again, if you choose to use your calculator, it's 11, then your button for combinations 6, and you'll get the same answer. Alright, this is going alright, I guess. I hope this is as much fun for you as it is for me. Alright. Identifying permutations and combinations. Now that we know what a permutation is and a combination is, a permutation is where order is not relevant. Or, I guess, for permutations, I guess, choosing 3 people for a subcommittee, we will have more. It'd be like me choosing for the Example 3. How many ways can a 3-person subcommittee be selected from a committee of 7 people? So here, we're choosing 3 from 7. And is this permutations or is it combinations? The answer is combinations. Because each of these 3 people, we're just picking them out of a hat. So it would be like me choosing Ingrid, Joe, and Rachel is the same as choosing Joe, Rachel, and Ingrid, or Rachel and Ingrid and Joe. Each of them don't have a specific role. They're just a group of people. So N is 7. We're choosing of 7 people. R is 3. So we're doing 7C3. Which is 7 factorial over 7 minus 3 factorial, 3 factorial. And that is 7 times 6 times 5 times 4 times 3 times 2 times 1. All over 7 times, 4 factorial. 4 times 3 times 2 times 1 times 3 times 2 times 1. The 4, 3, 2, 1 cancels out, and we're left with 7 times 6 times 5. Divided by 3 times 2 times 1. That'll cancel out, and that'll come out to 35. Or doing it on the calculator, it's 7, and then your NCR button for combinations 3, and you should get the same answer. Now, for the second part of example 3, how many ways can a president, vice president, and secretary be chosen from a committee of 7 people? Here, order does matter. Each person in the 3-person subcommittee has a specific role. Me choosing Ingrid as president, Joe as vice president, and Rachel as secretary is different from Joe as president, Rachel as vice president, and Ingrid as secretary, or Rachel as president, Ingrid as vice president, Joe as secretary. So it is a permutation. So, again, we still have n equals 7, and we have a president, vice president, and secretary. So we're still choosing 3 people, but it's a permutation this time. So it's 7p3. So it'll be 7 factorial, or 7 minus 3 factorial, which is 4 factorial. So we have 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. And we are left with 7 times 6 times 5, which is 210. Or if you're doing it on your calculator, getting the same answer, you do 7, then your button for permutation, and then 3. And you'll get the same answer. That is example 3. Alright. Example 4. 9 cards are are numbered with the digits 1 to 9. A 3-card hand is dealt, 1 card at a time. How many hands are possible in which order is taken into consideration and B, order is not taken into consideration? So for both of these, we have digits 1 through 9, so that's 9 choices of card, and we're choosing 3. So part A, order is taken into consideration, so it is a permutation. So each card will have a first card, a second card, and a third card, each with a specific role in the hand. So it'll be 9p3, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, or 6 times 5 times 4 times 3 times 2 times 1. Sorry. And then these will all cancel out, and we're left with 9 times 8 times 7, right? We have 9 possibilities and we're choosing 3. They can't be the same, so it's 9 times 8 times 7. Sort of what we saw kind of in the end of 7.3. And that comes out to 504. And on the calculator, it's doing it on the calculator. It's 9. Your button for permutations, 3. And you'll get the same answer. Part B, 9C3. It's a combination this time because order is not taken into consideration. It's just 3 hands in a 3 cards in a hand. Yeah. So it's a combination. So it's 7 times 6 times 5 times 4 times 3 times 2 times 1, or 6 times 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. The 6, 5, 4, 3, 2, 1 is cancelled out, and we're left with this, which we know is 504 over 6, which equals 84. So I guess the combination here is that for every 6 hand is the same, kind of. We'll have 6 of the same hands of those 3, so we get rid of those extra hands, kind of. That's the difference there. And on the calculator, that's 9. Then press your button for NCR. Press 3, and you will get the same answer, 84. And 504 for the last one. That is example 4. Example 5. A basketball team has 5 distinct positions. Out of 8 players, how many starting teams are possible if distinct positions are taken into consideration for part A? So here, we have 8 players, and we're choosing 5. N will equal 8. That's part A. R will equal 5. So we have distinct positions are taken into consideration. So we'll have a shooting guard, a quarterback. I don't know basketball stuff. Sorry. But yeah, we'll have 5 positions, I guess. So it's 8p5. Each of the players will have a position on the court field. So it'll be 8 factorial over 8 minus 5 factorial. So we'll have 8 factorial, or 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 minus 5 is 3, so we'll have 3 factorial. 3 times 2 times 1. Those will all cancel out. So we'll have 8 times 7 times 6 times 5 times 4. and that turns out to be 6,720. On your calculator, that is 8. Your button for NPR radio 5, and you should get the same answer, 6,720. Part B. Scroll back up actually. The distinct positions are not taken into consideration. But here we're still choosing 5 people from the 8, so our total N is still 8, and we're still choosing 5. The only difference is now it's a combination. So 8C5. So it'll be 8 factorial, 8 minus 5 factorial, 5 factorial. So we'll have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 6 times 7, sorry. That's 3 factorial, and then 5 factorial, 5 times 4 times 3 times 2 times 1. Again, the 3, 2, 1 will cancel out. We'll be left with this over this. You can cancel out the 5 and the 4. So we're left with 8 times 7 times 6 divided by 3 times 2 times 1. So really just 8 times 7, which is 56. Noticeably smaller than the permutation. And that's on your calculator, N8 NCR 5. So for a permutation was a lot bigger than the combination. And you'll see that as you're choosing more from more people, the difference between the two gets very large. Part C. The distinct positions are not taken into consideration. So it's combinations again, but either Mike or Ken, but no, not both, must start. So the first of our 5 people, basketball players, has to be Mike or Ken. So this one, we will use the addition principle, or the multiplication principle, since it's Mike or Ken and then the other 2. So it'll be 2 times our combination. But we remember either Mike or Ken, but not both must start. So after choosing Mike or Ken, we'd have 7 to choose from, but we couldn't choose the other, right? If we chose Mike for the first one, then we couldn't choose Ken. If we chose Ken for the first one, we couldn't choose Mike. So really, there are only 6 players left we can choose from after subtracting 8 from the 2. So N here equals 8 minus Mike and Ken. And we're choosing the 4 other people on the team. So it's 2 times 6 times 6 combination 4. So it'll be 2 times 6 factorial, or 6 minus 4 factorial, 4 factorial. And that becomes 2 times 6 times 5 times 4 times 3 times 2 times 1. 6 minus 4 is 2, so that's 2 times 1 times 4 times 3 times 2 times 1. These all cancel out. You can cancel out that 2 with that 2. We're left with 6 times 2 divided by 1, which is 30. And if you do this on the calculator, I'm not sure if the order of operations will hold on the calculators other than the TI-83s and above. The order of operations will hold for the TI calculators, but I'm not sure about the other ones. So on the other calculators, you might have to do the combination part first and then multiply it by 2 in the end. Alright, Super fun stuff. Example 6. Applications with a deck of playing cards. A deck of playing cards has 52 cards, 13 in each suit. We have 4 suits: diamonds, clubs, hearts, and spades. So we have 52 cards total. 4 suits, and then 13 cards in each suit. Also note that diamonds and hearts are red, and clubs and spades are black. I can't even read that. Black. It says red. Red. Alright. So that is what we need to know about playing cards. Also, that we have 3 face cards in each suit, and those are our jacks, queens, and kings. Our face cards. There are 3 in each suit. There are 4 suits, so there are 12 face cards total in the deck. So if you're unfamiliar with playing cards, that's basically what you need to know for it. I was in Bridge Club in elementary school, which is a popular card game. I wasn't very good at it, but I tried my best. So example 6. Example 6 says, from a standard 52 card deck, how many 7 card hands have exactly 2 clubs, exactly 3 cards, and 2 other cards that are not hearts or clubs, because we only have exactly 2 clubs and 2 hearts. So for our exactly 2 clubs, there are 13 cards in each suit, so we'll have 13, and then we're choosing 2, and here order doesn't matter. When we're doing these deck of cards and you get a hand, order will not matter unless it is specified, and that goes for most of the problems. So if order doesn't matter, we are dealing with combinations. So there's 13C2, which is 13 factorial, or 13 minus 2, 2 factorial times 2 factorial, and that ends you up with 13 times 12 over 2 times 1, which is 78, and on your calculator that's 13, then your button for combinations 2, and that'll give you 78. So that's our exactly 2 clubs. And then we have our exactly 3 hearts, and again order doesn't matter. So 13 cards in each suit. This time we're choosing 3. Order doesn't matter again. So it's combinations. 13C3. That'll be 13 times 12 times 11 divided by 3 times 2 times 1. And that gives us 286. And on the calculator, 13, then your button for combinations 3. So we've done the 2 clubs and we've done the 2 and the 3 hearts. And now we need the 2 other cards. And these 2 other cards can't be hearts and they can't be clubs. So they're either going to be spades or diamonds. So n is 13 plus 13, our number of spades and our number of diamonds. So it's 26 and we're choosing 2. And again, order doesn't matter. So it'll be 26C2, which is 26 times 25 over 2 times 1, which is 325. Now on your calculator, that's 26C2. And then our solution, because we have exactly 2 clubs and then exactly 3 hearts and exactly 2 other cards, our final answer will be, I don't know if I can fit it in here, but 13C2 times 13C3 times 26C2. See if I can split that up. And that is our 3 answers: 78 times 286 times 325, which equals our final answer, 7,250,100. That's a lot of combinations. I don't know if you've heard, like, if you shuffle a deck of cards, the chances when you shuffle a deck of cards, your shuffle, what you end up with, the order it's in, is unique and probably has never been seen before, because it is 52 factorial would be the order it's in, which is, I think, like 8 with 87 zeros after it, which is humongous. So now example 7. Here, applications with basic counting principles. Our catering service offers 8 appetizers, 10 main courses, and 7 desserts. A banquet committee accepts 3 of the 8 appetizers, 4 of the 10 main courses, and 2 of the desserts. Here, it doesn't matter what order the food comes in, so order doesn't matter. So for the appetizers, we are choosing from 8, we're choosing 3. So it'll be 8C3, which is 8 factorial over 5 factorial, 3 factorial. Comes out to 56. For our main course, we are choosing from 10, 4, so it'll be 10C4, so it'll be 10 factorial over 10 minus 6, or 10 minus 4, which is 6 factorial times 4 factorial, which is 210. And then for the dessert, we have n total, and we're choosing 2. So it'll be 7C2, and that is just 21. So our final answer, using our multiplication principle, since we have an app and a main course and a dessert, will be 56 times 210 times 21, and that gives our final answer 246,960. That is example 7. Try to get a little bit quicker now. Okay, for example 8, an electronics store receives a shipment of 30 graphing calculators, including 6 that are defective. 4 of these calculators are selected for a local high school. How many selections can be made? So here N is 30, R is 4. Does the order of the calculators matter here? No. Order doesn't matter. So it's a combination. So we'll be doing 30C4, which is times 30 times 29 times 28 times 27 divided by, and that comes out to 27405. And then how many of these selections, so that's part A. And part B, how many of these selections contain no defective calculators? Here N is going to be 30 minus 6 is 24, and we're still choosing 4, so it'll be 24C4 on your calculator. 24C4 gives us 10,626. So yeah. So we'll see in probability how many. Our answer for B divided by answer A will be the probability of the school getting a defective calculator, which we will see in the next section on chapter 8 in our dealings with probability. Our last and final, our final example, 9, is in 4 parts. Here, suppose we have 6 female and 5 male applicants have been successfully screened for 5 positions. In how many ways can the following compositions be selected? Here, for part A, we have 3 females, 2 males. So we have 6 females, 5 males. So from 6, we are choosing 3. For all of these, order doesn't matter, because these 5 positions are likely all the same. So our number for those 3 females, C combination 6C3, which is 20. And then for the 2 males, we have 5 males and we're choosing 2. So it's 5C2, which is 10. So for part A, using our addition or multiplication principle, 20 times 10, 200 different ways is our answer for part A. For part B, 4 females, 1 male. N is 6, R is 4. So 6C4, which is 15. And then 1 male. A thing about combinations is, if we have 5 and we're choosing 1, there's only 5 ways to choose 1 person. Right? If we have 5 people, there's only 5 ways to choose 1 of them. So 5C1 is 5. So our answer for part B is 15 times 5, which comes out to be 75 by the multiplication principle. For part C, 5 females, and a 6, R is 5. Here, same as before, kind of. How do we choose 5 females? How many ways can we choose 5 females from 6? That's kind of the same as not choosing one of them. So 6C5 is going to be 6 because it's like we're not choosing one of them. And then pens. Sorry about this. Sorry. It's a technical difficulty here. Insert blank page. Then we go to pens. So for part D, or no, we're still on part C, sorry. Well, yeah, it's just going to be 5 because it's just all 5. I'll rewrite that. For C, we're just choosing 5 females from, so N is 6, R is 5, 6C5 is 6 because just like before, yeah. And we have no males, so our answer is just 6 for that one. D, 5 people. So here, we just have 5 people. N is our men and women, which is 11, and R is 5. Order still doesn't matter. So it's 11C5, which is 462. And now, for part E, at least 4 females. That means we have 4 females or 5 females. And in part B, we saw that that was 15. And in part C, that was 6. When it's OR, that's the addition principle. 15 plus 6 is 21. And that is our answer for part E of example 9. Our last example for this section. Sorry about